So for problem number 8, we've got a square loop of wire and it's moving at a constant speed across a uniform magnetic field. The first thing we're going to do is find the direction of the induced current in the loop, and this is just as it enters. So what we notice is that as it's coming into the magnetic field, the flux is increasing. So as it's coming in, we've got B increasing, and we want to oppose that increase in B. So we want to have an induced current that is going into the page rather than out of the page. And so we have a current in the beginning that is going clockwise, and that causes a magnetic field. Let me get rid of that. Going into the page. So clockwise is our answer. So let's do part B, the magnitude of the induced current in the loop. That is I equals EMF over R. EMF is equal to negative d flux over dt. We've already defined the direction, so let's just focus on finding the magnitude. And that is BA cosine theta, but because the normal coming out of the plane of the loop is parallel to the magnetic field, we know that that cosine theta just cancels out. Now we need to think about what's changing, and I forgot to put my ddt in here. So I need to figure out what part is changing. The magnetic field is staying the same. And even though the area of the loop isn't changing, as it moves into the field, the length, or we can even call it the width here, that is filling the loop is increasing. And so we know this length stays the same, but we've got a change in area because the magnetic flux is filling more and more area over time. So we are going to write this as B. The area equation would be LDL, sometimes using the same variable, even though the lengths are the same, can be confusing. So if you wanted to, you can call this X instead of L. And then we can, and then we can substitute that into our equation. We still have our dt, and this, as we've gone over many times, is a change in distance over change in time. That's just velocity. So EMF is BLV, but our current is BLV over R. All right, the direction and magnitude of the magnetic force required to move the loop into the field. So first of all, we experience a force when we've got a set of charges moving. And so since the velocity, let me just clear out some of this stuff. Since the velocity is moving to the right, and as we enter the field, we only have this section within the field. We know that the current in that section is going counterclockwise. So in that section, it's going down. And since the current is going down and the magnetic field is coming out of the board, we experience a magnetic force to the left. Now, the magnetic force, you can do the work for this. The magnetic force, if a little bit of the top and bottom are in the field, they're going to go in equal and opposite directions. And so the forces in the y direction cancel out. But this last segment here is not in the field yet. And so it's not going to experience a force unless it's moving in a magnetic field. So all we're focused on is the force on this first section of the wire that enters, and that's going to experience a force to the left, and that's the direction, so left, and then the magnitude of force required to move it to the left would be your magnetic force equation. FB is equal to ILB, and we've got our current as BLV over I. L is going to be the length of the loop that we're analyzing, which is this length of loop, so that's just L. The reason why we're not taking the others into consideration again is because each loop is going to experience a force in a different direction, and we already know that this side and this side are going to cancel out. I just noticed a notation error here. This is BLV over R. Then we've got our length L, and then the last piece of our equation is this B. So now we've got B squared L squared V over R. Okay, so now we're looking at the time interval when the loop leaves the field. Determine the following: the direction and induced current in the loop. So we've got a loop here, and now it is leaving the field. What we notice is that what we had when it was in the field was a full magnetic flux out of the page, and now that loop is leaving, that magnetic flux coming out of the page is going to decrease. So in order to oppose the change, we want to create a current that induces a magnetic field out of the page as well. And so that would give us a counterclockwise current, which gives us more magnetic flux out of the page. So this one is counterclockwise. The magnitude of the induced current in the loop, well, we still have the same change in length, right? This length is going to decrease now as it comes out of the page. So it's still going to be the same magnetic field, the same length, which is this length right here, and then the same change in X. So we end up having the same current. It's going to be BLV over R. That's supposed to be a V. It's just going to go in the opposite direction. And then the direction and magnitude of the magnetic force required to move the loop out of the field. This one is going to be, again, the side of our loop here does not experience a force because it's no longer in a magnetic field. The top and bottom, as we stated, is going to experience equal and opposite forces, so that net force ends up canceling out in the y direction. And then the current, as it goes down on this side, this is the one we really want to focus on, is going to experience, because the current's going down and the magnetic field is coming up, it's going to experience a force pulling to the left, and it's going to be again to the left, and the magnitude is going to be the same because it's again ILB. Again, we established the current is the same, the length is the same, that's the length of the wire, and the magnetic field is the same. So it's going to be exactly what we got in part C. Okay, on the axis below, graph the induced current and magnetic forces as a function of position. So let's get those graphs. And what we're going to analyze first is as the right side of the wire enters, it's going to be at L, and it'll continue to enter up until 2L until it gets or I guess that was a little bit too big, 2L's right about here, until it starts experience a constant magnetic field, which therefore has no change. So from L to 2L, we are going to go, what did we say in the beginning? Clockwise. So we're going to go clockwise here. Let me use the highlighter. Once it's fully inside, then the magnetic field isn't going to change until it gets to 3L and it starts decreasing magnetic field. So anywhere in the middle up until 3L is going to be 0. And then at 3L, we established it goes counterclockwise. So it's going to be equal in magnitude, but at the top. And then once it hits 4L, it's basically out of the magnetic field. So it'll look like this. The same idea is whenever it has a change of magnetic field, we induce a current. That induced current is going to apply a force, and the force we established was left. So between L and 2L, we've got a force going to the left, and then between 3L and 4L, we've got another force going to the left, and then everywhere else, there's no current, so it's just 0.